Hello, beasties. Sorry, I just got tired of looking at my face every time I edit these things, so here you go. I wanted to just kind of go over this sheet because it's kind of a summary of everything that you need to learn for this chapter, and there's a lot of little points that I'm hoping don't get missed. So, as we're heading toward the end of the chapter here, just to go back over from the beginning, we started with radical functions. So that's where we've got y equals root x. And the first thing that we noted was that obviously we can only deal with positive values for y. So if I were to have a graph that looked like that, and it maybe, I don't know, look like that, we're only dealing with the values that are above this line. So when it says that we can only have positives, we're not going to deal with these values, and therefore we will only be looking at what's in here and what's in here. But we won't be looking at any values between there, because the only value we have is a negative value for y, so it can't possibly have a root value. So that's when we have y equals the square root of f of x, another function, right? So we keep the x values stay the same, the y value gets plotted, I guess the root of the y gets plotted over the same x value. So that leads us to our next portion, which is in here it says we have the same points at 0 and 1. Because if this were my graph, I would have a point here, and if that was 1, well, let's actually change that a little bit. Say this is 1 here. That means I'm going to have a point here on my new graph. I'll have a point at 0 because the square root of 0 is 0. I'll have a point where it hits 1, same point, because the square root of 1 is 1. And then we talked about the fact that if it's a decimal, like 0.5, the square root of a decimal is actually a larger number. Because, for example, I guess I should have used 0.25, because the square root of 0.25 is actually 0.5. So the answer is bigger, which means we're going to have a curve over the line. We don't have to actually put that in really specifically. We're just going to put it over the line because we know that it is a larger value. And we're just doing a sketch. So to continue with this, I'm going to put another point here where it's 0 and another point here where it's 1. And I know that this is going to be under the line, and I know that this is going to be over the line, so just roughly sketching in those points. If I had a graph that gave me larger values that I could just take, like in this point, I would take the square root of this point and plot it here. In this case over here, let's say this line goes up really far, and before it leaves this graph, I have 4 here. So I'm going to plot 0 and 1. I'm going to put a little curve over the line. Gets kind of messy when it's really close. And then I'm going to go, okay, over here, that's where it's at 4. So I'm going to drop that down. Sorry, this is a rough sketch. Drop that down to 2. Because it's the square root of 4. Then I'm just going to run my line through it, and there goes the sketch. I hope you can see that 4. Anyway, you get the idea. We have same points at 0 and 1. We put a curve above the line between 0 and 1, and then for any other y values, we find one with a perfect square, like we did with the 4, and get the 2. If you don't have any with a perfect square, you'll just have to calculate what the square root is. And then we'll plot it over the same x and connect the points. So that's basically the beginning of this bit here. It talks about domain and range may differ from the original graph. So on this one, we had the original domain is all points, so x is in the realm of R because there was no limitations. It just keeps going in the horizontal direction. And the range of this graph would have also kept going because it's got this line descending, this line going up, no limits. So y was also in the realm of R. But the root graph, the one that we plotted, isn't that way. So if I look at the domain, I am interrupted right here. So there are no values for x between 0 and, let's say that's a -2. Well, that looks like a little less than, well, we'll call it 0. So we would say that x is in between -2 and 0. That means it can be less than or equal to, I do that wrong? So x, nope, you have to move them that way. Or your book will actually say that x is greater than or equal to 0 and x is less than or equal to -2. Either way, writing it is just saying that there is no value between -2 and 0 for x, so the domain is limited. The range also would be limited because you cannot have a negative value for y. So y is greater than or equal to 0, but not going to be below it. So you can see from this example that the domain and range from the original are different from the graph that we plotted. Moving on to the last part. Now this is, we've spent more time with this stuff. This is when I have a rational function as opposed to a radical function. And this is where we've got all these rules that we deal with in terms of asymptotes. So the first thing we want to do is recognize that g of x, the bottom, can't be 0. So we look at the non-permissible values when that would be 0. Obviously we can't have them, so we've got to deal with them. We have a vertical asymptote when that would be 0, and there are no common factors. So that one's pretty simple. Vertical asymptote means there's going to be a line that it gets close to but doesn't touch, and if there's no factors, that's what we're dealing with. But it gets a little trickier when we're dealing with a whole. So if I've got a function, for example, y equals, I'll just keep this really, really simple, x plus 1, x minus 1, all over x minus 1, then I've got two factors, one on top, one on bottom, that cancel out. So that means my resulting line, well, I guess my x cannot be positive 1, but it's not going to be an asymptote because when I cancel this out, I've got what's left, and I just specify as long as x doesn't equal 1, then this will work. Now, they want you to actually find the whole, the coordinates of the whole, not just the fact that x can't equal 1, but where is that in the graph. So when you do that, that's where it says to find x and y of the whole, plug x into the simplified formula. So plug this into this. So y equals, we'll write whole, y equals 1 plus 1, so that gives us 2. So the whole is going to be at 1 and 2 in this case. So when you plotted it, you would actually find a graph or find a spot at 1 and 2, and you're going to have a hole there. All right. That pretty much deals with our vertical asymptotes. Our horizontal asymptotes are pretty simple, straightforward, just two rules. So if I have x over x squared, for example, where the degree of the numerator is less than the degree of the denominator, then I'm going to have an asymptote at y, or a horizontal asymptote at y is 0. If I have a number that matches, so x over x, x squared over x squared, then I'm going to be looking right here to find out what the number is, because that's what my number is going to be for my horizontal asymptote then. So, for example, if I have 2x over x, then my horizontal asymptote is just going to be 2. So those are the two rules dealing with the horizontal asymptotes. The oblique asymptote is going to be where I have x squared over x, where my numerator is actually a larger degree than my denominator. So in this case, I'm going to actually have to use synthetic division to figure that out. If I had, for example, two x squared plus 3x minus 5 all over x minus 1, I can see that I've got my x squared over my x, and I can see that...
Teresa, can you please go to the
Oh,
staff room?
announcements,
Teresa,
isn't that fun?
staff room?
You guys hear that? Brings back all warm and fuzzy memories. So I'm just going to do synthetic division here. 2, 3, negative 5. Bring down the 2. 1 times 2 is 2. That adds to 5. 1 times 5 is 5.
They can have a quick sit down with secondary folks in the gym, I guess.
And in this case, there's no remainder. The beauty of this part is that we don't care about the remainder anyway, because as the value of x goes up, I just put in my x there because this is x squared, the remainder's not going to matter, so we actually just get rid of it. So what we found here is that the oblique asymptote is at y equals 2x plus 5. So if I were to draw my graph, I would use my slope and my intercept. I would go 1, 2, 3, 4, 5, right there. Actually, let's just move that down a bit. 1, 2, 3, 4, 5. That's my starting point, and then it goes up 1 over 2. So I would come back this way. And then I've just got my nice straight line, but it's an asymptote, so it's going to be a dotted line. There you have it. We've got vertical asymptotes, horizontal asymptotes, and oblique asymptotes. This is pretty much all you need to know for Chapter 2. You're going to have a portion of your test where you don't get to use a calculator, so make sure you're not cheating.